Hey everyone, and welcome. Today, we're going to pull back the curtain on something that's totally invisible, but, powers pretty much our entire world electricity. It can seem super complex, but really, it all kicks off with a simple and sometimes shocking little spark. So, let's dive in. You know the feeling, right? You're walking across a carpet, maybe shuffling your feet a little, you reach for a metal doorknob, and zap, you get that tiny jolt. Well, that little spark, that thing that's a minor annoyance, that's actually our first clue to understanding the whole mystery of electricity. So what in the world is that spark? It's a little thing called static electricity. And it happens because of a super fundamental property of matter, a property that powers everything from your phone to the lights in your house. And that property is called electric charge. Okay, so what is charge, really? The easiest way to think about it is, well, it's kind of like mass. You know how a bowling ball just has mass? It's part of what makes it a bowling ball. It's the same deal with the tiny particles that make up everything, electrons and protons. They just have electric charge. It's a core part of their identity. Now, here's where it gets interesting. These charged particles, they aren't just chilling out. Nope. They're constantly interacting with each other, and they follow a really strict but really simple set of rules. It's like a tiny drama playing out on a microscopic scale all the time. And here it is, the one rule to rule them all. It's a tale of attraction and repulsion. Charges that are the same, say two positives, they push each other away. They repel. But opposite charges, they pull each other closer. They attract. This simple push and pull is the engine behind absolutely everything electrical. And this whole push and pull dance isn't random at all. It's actually perfectly predictable. The strength of that push or pull really just depends on two things: how much charge the particles have and how far apart they are. The point is, there's a beautiful mathematical order to this invisible world. Okay, so we know what charge is and we know its basic rules of engagement. But how do we get from these little particles pushing and pulling each other to a useful electric current that can, actually power something? What gives these charges the motivation to get up and go? The answer is something called potential difference, but you probably know it as voltage. Honestly, the best way to think about voltage is just as electrical pressure. It's the force, the oomph, that pushes the charges to move from one spot to another. Without that push, nothing flows. Simple as that. And when that voltage gives the charges a good push, we get what's called an electric current, which we measure in amps. So if voltage is the push, then current is the actual flow. It's literally just a measure of how many of those charges are zipping past a certain point every single second. Let's make this even simpler with a classic analogy. Just picture water moving through a pipe. The pressure that's forcing the water to move, that's our voltage. And the amount of water actually flowing through that pipe, that's our current. See? This simple picture makes these invisible ideas feel a whole lot more real. All right. Every good story needs a little conflict, right? Well, just like water in a pipe runs into friction, electric current doesn't always get a free pass. It runs into obstacles, things that try to slow it down. And that obstacle has a name: resistance. Resistance, which we measure in ohms, is exactly what it sounds like. It resists the flow of current. So materials like copper wire are fantastic conductors. They're like a wide open highway with super low resistance. But materials like rubber, they're insulators. They have crazy high resistance and pretty much bring the flow to a dead stop. Let's jump back to our water pipe for a second. If you wanted to slow down the water, what would you do? You could make the pipe narrower, right? Or maybe make the inside rougher. That's exactly what resistance does to an electric current. It's the narrowing of the path that makes it tougher for the charges to squeeze through. And all this leads to a really important relationship. Think about it. If you're trying to push the same amount of current through a path with more resistance, what do you need? You need a bigger push. This perfect relationship is captured in a beautiful, simple little formula called Ohm's law. Voltage equals current times resistance. This thing is like the master key to designing and controlling pretty much every electrical circuit out there. So we've got the push, we've got the flow, and we've got the obstacle. Now it's time for the fun part. Let's put all these pieces together and build something that actually does something. Let's make a simple circuit. To talk about circuits, we use a simple visual language, kind of like a blueprint. A cell or a battery, that's our voltage source. A light bulb gives us resistance, and hey, it also gives us light. And a switch is like the gatekeeper, opening or closing the path so the current can flow. So how do we put these together? It's totally logical. First, you need a power source, right? That's our cell. Second, you need something for that power to do, like lighting up a bulb. Third, you need a way to control it. That's our switch. And finally, you just connect everything together with wires to make a complete closed loop for the current to run around. And voila, here's the final result. When we close that switch, the path is complete. The voltage from the battery pushes the current through the wire, and it flows into the bulb's tiny filament. Now that filament resists the flow, and here's the magic. That resistance creates friction, which creates heat, and that heat makes the filament glow super bright. The current then travels back to the battery, and the whole loop starts again. A complete working circuit. And that one simple idea, resistance creating heat, is one of the most important ways we use electricity every single day. It's not a bug, it's a feature. It's exactly how your toaster works, how an electric heater warms up your room, and how an iron gets hot enough to press your clothes. We are constantly using this obstacle to do really useful stuff for us. So what's the big takeaway here? It's that our entire electrified world, from the massive power grids down to the tiny microchips in your phone, runs on this one beautiful, simple idea: a flow of tiny charges given a push by voltage and controlled by resistance. We've managed to master these simple rules to build our entire modern world. And that just leaves one really cool question to chew on. Now that we know how it works, what do you think will be the next revolutionary spark of innovation? Thanks so much for joining me.